From the dawn of human civilization, people have looked up at the night sky with a mixture of wonder, curiosity, and fear, trying to understand what lies beyond the faint shimmer of the stars. Every ancient culture built myths and legends around the heavens, seeing gods, monsters, and cosmic forces in the patterns of the stars and planets. But what began as imagination slowly transformed into science, as centuries of observation and calculation revealed the true nature of the cosmos. The Earth, once believed to be the center of all creation, was shown to orbit an average star, which itself was only one of hundreds of billions in a galaxy adrift in a universe too vast for the human mind to fully comprehend. And yet, even as telescopes grew more powerful and scientific theories more advanced, there remained a boundary that no human could cross, a physical limit to how far we could see and how much we could know. That changed in 1977, when two robotic explorers, Voyager 1 and Voyager 2, were launched into the great unknown. Unlike anything that came before, they were not built merely to orbit Earth or land on the Moon, nor even to study a single planet. They were designed for a grand tour of the solar system, a journey across billions of miles, to reveal worlds we had never truly seen, and to send back knowledge that would transform our understanding of existence itself. The timing of the Voyager missions was more than scientific opportunity, it was cosmic luck. Once every 706 years, the outer planets align in such a way that a single spacecraft can use their gravity like a slingshot, moving from one to the next, with minimal fuel. This rare planetary arrangement offered humanity a once-in-a-lifetime chance to send a machine on a journey across the solar system and beyond. Voyager 1 and 2 seized that opportunity, venturing farther than any human-made object in history. Their missions were ambitious: to study Jupiter, Saturn, Uranus, and Neptune up close, to map their moons, to analyze their atmospheres, to understand their magnetic fields, and to carry humanity's message into interstellar space on the famous Golden Record. In essence, these spacecraft were more than machines. They were time capsules, ambassadors, and pioneers. The discoveries that followed were not only beyond expectation, they were beyond imagination. No one anticipated that Io, one of Jupiter's moons, would explode with volcanic fury more powerful than anything on Earth. No one thought Europa would hide an ocean beneath its icy crust that could hold twice the water of all Earth's seas combined. Saturn's rings, long admired from Earth as seemingly solid and smooth, turned out to be composed of countless icy fragments shaped by the invisible hand of gravity. Titan revealed itself as a world with lakes of liquid methane and a dense orange atmosphere, resembling a young Earth, while Enceladus erupted with geysers of water that hinted at another hidden ocean below its frozen shell. Uranus and Neptune showed magnetic fields tilted and twisted in ways that defied the textbooks, and Neptune's storms roared with winds faster than sound, despite its great distance from the Sun. Every planet, every moon, every encounter overturned assumptions and demanded new theories. Yet, the Voyagers were not content with revealing only the worlds of our solar system. Decades after their launch, long after they had passed the giant planets, they reached the very edge of the Sun's influence. Voyager 1 became the first human-made object to cross into interstellar space in 2012, followed by Voyager 2 in 2018. They entered a realm no human had ever imagined exploring within our lifetimes: the space between the stars, where the solar wind fades and the galaxy begins. Today, both spacecraft continue to send back faint signals across billions of miles, carrying instruments that still function against all odds. Each transmission represents not just data, but a profound reminder of what humanity is capable of when it dares to dream beyond the boundaries of Earth. The story of Voyager is at its heart, the story of humanity's hunger for knowledge and exploration. It is proof that curiosity can outlast generations, that a machine built in the 1970s can still shape the science of the 21st century, and that our reach can extend farther than we ever thought possible. More than just spacecraft, the Voyagers are a declaration that humanity is not confined to Earth, nor to the orbit of our star, but is destined to venture outward, carrying with us questions, hopes, and a golden message to any who might listen in the endless dark. This introduction is not merely the beginning of a mission summary, it is the opening to a saga that has redefined our place in the cosmos. In the early 1970s, space exploration was at a crossroads. The moon landings had captivated the world and proven that humanity could accomplish what once seemed impossible. But the question remained, what came next? The inner solar system had been touched, Mars and Venus probed, and yet the vast outer reaches of our cosmic neighborhood remained shrouded in mystery. Jupiter's storms, Saturn's rings, Uranus's tilted axis, and Neptune's icy winds were still little more than vague impressions drawn from telescopic observations. To reach them directly seemed beyond reach, both in terms of technology and resources. Yet in this moment of uncertainty, a discovery was made that would change everything. At NASA's Jet Propulsion Laboratory, a graduate student named Gary Flandreau realized that once every 17.6 years, the four giant planets align in such a way that a single spacecraft could visit them all in sequence. By using gravitational assists, slingshot maneuvers, where the spacecraft borrows speed and trajectory from a planet's gravity, it was theoretically possible to leapfrog from Jupiter to Saturn to Uranus and finally Neptune in a matter of years, rather than centuries. It was not just a scientific opportunity, it was a cosmic invitation. Humanity had one chance in a lifetime to ride this planetary alignment, an opportunity that would not come again until the year 20. The significance of this revelation was enormous. Missions to the outer planets had always been considered improbable because of the sheer distance involved. A spacecraft powered by conventional means would either take far too long or require an impractical amount of fuel. But gravitational assists turned this impossible dream into something achievable. Suddenly, the outer solar system was within reach, and the concept of a ground tour of the giant planets was born. NASA quickly realized that if they missed this alignment, it would be lost to future generations. Despite financial constraints and political hesitation following the Apollo program, the case for this mission was compelling. Not only could it answer fundamental questions about the planets themselves, but it also represented a bold continuation of human exploration at a time when public interest was beginning to wane. Turning the idea into reality, however, demanded unprecedented engineering. A spacecraft would need to survive, not just for years, but potentially decades in the harshest conditions imaginable. Solar panels, which powered most probes up to that point, were useless so far from the sun. The answer lay in radioisotope thermoelectric generators, nuclear power sources capable of steadily producing electricity by converting the heat of decaying plutonium into usable energy. This would allow the spacecraft to function even at the distant orbit of Neptune, where sunlight is a faint glow. Communications were another challenge. The further a spacecraft travels, the weaker its signal becomes, until it is drowned in cosmic noise. To overcome this, NASA relied on the Deep Space Network, an array of massive antennas spread across 3 continents, designed to pick up the faintest whispers from billions of miles away. The spacecraft themselves had to be built with a level of redundancy and durability never attempted before. They would carry twin sets of critical systems to guard against failures. Their instruments, cameras, and detectors had to be shielded against radiation belts so intense that they could fry electronics in minutes. Every part was tested to extremes, because once launched, there would be no fixing what broke. These challenges were daunting, but the potential rewards were irresistible. For the first time, humanity could hope to see the swirling storms of Jupiter up close, to examine Saturn's rings, not as a blur but as a system of countless icy particles, to glimpse Uranus's strange sideways spin, and to watch Neptune's supersonic winds tearing across its blue surface. Beyond the science, there was a deeper layer of meaning. This mission was a statement that even in times of uncertainty, humanity would not stop reaching outward. It was an act of vision, a declaration that we were not bound by the limits of our present, but driven by the possibilities of the future. Voyager 1 and Voyager 2 were not merely machines. They were emissaries built to last, vessels carrying the ambition of a species that longed to see beyond its cradle. The decision to build and launch them was not just about exploring planets. It was about answering the timeless call to explore the unknown, to seize a fleeting alignment of worlds, and to send something of ourselves into the deep, silent dark of interstellar space. From the very beginning, the Voyager project was more than a mission. It was a bold leap into history. When the two Voyager spacecraft launched in 1977, they carried with them not only the weight of extraordinary engineering, but also the boundless curiosity of humanity. Their first target was Jupiter, the largest planet in our solar system, and a world that had fascinated astronomers for centuries. Up until that moment, Jupiter had been studied only through telescopes, its swirling cloud bands and the great red spot observed from afar but never directly examined. As Voyager 1 and Voyager 2 approached the gas giant, what they revealed was beyond anything scientists had imagined. The spacecraft's cameras captured the planet in astonishing detail, uncovering a world of violent storms, shifting colors, and complex atmospheric dynamics. The Great Red Spot, long thought of as just a vague reddish oval, was revealed as a gigantic storm larger than Earth itself, raging for centuries, with winds exceeding hundreds of miles per hour. New storms, smaller but equally ferocious, appeared across Jupiter's surface, showing that the planet's atmosphere was far more dynamic than previously understood. Lightning flashes were detected, confirming that electrical activity crackled within those massive clouds. These discoveries transformed Jupiter from a distant gas ball into a living, breathing world of turbulent weather systems. But perhaps the most groundbreaking revelations came not from Jupiter itself, but from its moons. Until Voyager, the Galilean moons Io, Europa, Ganymede, and Callisto were thought to be frozen, largely inactive worlds. Instead, Voyager uncovered landscapes that rewrote the rules of planetary science. Io, for instance, stunned the world by revealing itself to be the most volcanically active body in the solar system. Instead of a static, frozen surface, Voyager's images showed towering plumes of sulfur erupting hundreds of kilometers into space, constantly reshaping the moon's surface with rivers of molten rock. This discovery alone shocked scientists, because it proved that tidal heating caused by the gravitational tug-of-war between Jupiter and its moons could drive incredible geological activity. Europa was equally fascinating. Voyager's images revealed a cracked and fractured surface, resembling shattered glass floating on an ocean. The patterns suggested that beneath Europa's icy crust lay a subsurface ocean of liquid water, kept warm by the same tidal forces that fueled Io's volcanoes. That possibility, that an ocean larger than all of Earth's combined could exist on a distant moon, sparked one of the most enduring questions in planetary science. Could Europa harbor the conditions necessary for life? Ganymede and Callisto added more surprises. Ganymede, the largest moon in the solar system, was revealed to have complex surface features, a mix of older, heavily cratered terrain and newer, grooved regions, hinting at geological processes in its past. Callisto, though more heavily cratered and seemingly less active, provided valuable clues about the history of impacts and the evolution of outer solar system bodies. Together, these moons proved that the Jovian system was not just a collection of cold, dead rocks, but a miniature solar system filled with diverse worlds, each with its own mysteries. Beyond the moons, Voyager also discovered Jupiter's faint ring system, something no one had expected. Unlike Saturn's bright and extensive rings, Jupiter's were thin, dusty, and nearly invisible from Earth. Their discovery hinted that ring systems might be more common around giant planets than previously thought. The flyby of Jupiter was not only a triumph of exploration, but also a dramatic demonstration of the power of gravitational assists. As Voyager 1 swung past Jupiter, it stole a tiny fraction of the planet's momentum, accelerating toward Saturn and bending its path with precise accuracy. Voyager 2 would follow its own trajectory, also using Jupiter's immense gravity to slingshot deeper into the solar system. This technique, once a theoretical possibility, was now proven in practice, showing that spacecraft could hitch rides from the planets themselves to travel vast distances without expending enormous amounts of fuel. It was a moment that combined scientific wonder with engineering mastery, and it set the stage for the rest of the mission. Perhaps what made Jupiter's encounter so memorable was how it captured the public imagination. The images sent back to Earth were displayed in newspapers, on television, and in classrooms, showing people for the first time the true faces of worlds they had only dreamed about. Suddenly, the gas giant and its moons felt close, familiar, and real. The stormy clouds of Jupiter, the fiery volcanoes of Io, and the icy cracks of Europa became part of a shared human experience, reminding everyone of the vastness and complexity of the cosmos. Scientists were thrilled, but so too were ordinary people who could look up at the night sky and know that those bright dots had secrets that humanity was finally beginning to uncover. The Jupiter encounters marked the beginning of Voyager's transformation from a bold scientific mission into a cultural phenomenon. It showed that exploration was not just about answering technical questions, but about igniting a sense of wonder, connecting people on Earth to the mysteries of the universe beyond. In many ways, the Jupiter flybys were the opening act of a grand cosmic story, one that would only grow more extraordinary as the Voyagers pressed onward to Saturn and beyond. After the breathtaking discoveries at Jupiter, the Voyager probes continued their odyssey toward Saturn, and what awaited them there proved to be equally, if not more, astonishing. Saturn had long been admired from Earth, through telescopes, for its iconic rings and serene golden hue, but Voyager revealed a world far stranger and more complex than anyone had dared to imagine. As Voyager 1 approached in late 1980, its cameras began capturing the planet's rings in unparalleled detail, and what seemed from afar like a smooth, flat structure instead unfolded into a dazzling system of countless individual particles, from dust grains to house-sized boulders, orbiting in intricate patterns. Voyager discovered that Saturn's rings were not a simple set of broad bands, but were instead composed of thousands of ringlets, weaving together in an extraordinary ballet governed by gravity and resonance. Among these countless ringlets were mysterious dark gaps and divisions, some created by the gravitational influence of nearby moons, others the result of complex, still not fully understood interactions between ring particles themselves. This revelation transformed Saturn's rings from a pretty spectacle into a laboratory of celestial mechanics, where the subtle push and pull of gravity could be studied on a scale visible to human instruments. Voyager also uncovered the bizarre and beautiful phenomena known as spokes within Saturn's rings. These dark radial streaks appeared to form and vanish mysteriously, stretching across thousands of kilometers. Scientists hypothesized they were caused by charged dust particles levitated above the rings by Saturn's magnetic field, an idea that highlighted how dynamic and interactive the ring system truly was. Rather than being static debris orbiting in silence, Saturn's rings turned out to be alive with processes influenced by gravity, electricity, and magnetism. This alone would have been enough to cement the Voyager encounters as historic, but the discoveries extended far beyond the rings themselves. Saturn's moons, long thought of as little more than cold, frozen bodies, revealed themselves to be a gallery of alien worlds, each with its own personality and story. Titan, the largest moon, became the crown jewel of the Saturn system. As Voyager's instruments peered through its hazy orange atmosphere, they detected a thick blanket of nitrogen and methane, unlike anything seen on another moon. The atmosphere was so dense that Voyager's cameras could not penetrate to the surface, but the presence of hydrocarbons suggested that Titan might harbor lakes, rivers, or seas of methane and ethane. The idea that a moon could have a thick atmosphere, with chemistry resembling that of early Earth, electrified scientists and sparked decades of speculation about whether Titan might host prebiotic conditions or even exotic forms of life. Titan would eventually become the target of future missions like Cassini-Huygens, but it was Voyager that first revealed its tantalizing mysteries. Other moons astonished the scientific community with their variety. Enceladus, a small icy world, showed an unusually reflective surface, indicating that fresh ice was constantly resurfacing it, a hint at internal activity. Menes, with its enormous Herschel crater, looked eerily like the Death Star from science fiction, instantly captivating the public. Tethys, Dione, and Rhea each revealed heavily cratered terrains, bearing the scars of ancient impacts, but none shocked observers more than Iapetus, with its bizarre two-tone coloration, one hemisphere dark as coal, the other bright as snow. This strange dichotomy suggested processes of dust accumulation and sublimation at work, making Iapetus one of the most visually striking objects in the solar system. Then there was Saturn itself. Voyager revealed atmospheric features beyond the soft, hazy look that telescopes had shown. Storms, jet streams, and banded cloud structures covered the planet, driven by high-speed winds that reached hundreds of miles per hour. The spacecraft's instruments detected powerful auroras shimmering near the poles, caused by the interaction of Saturn's magnetic field with charged particles from the solar wind. The magnetic field itself turned out to be nearly perfectly aligned with Saturn's rotation axis, an oddity that challenged existing models of planetary magnetism. Voyager showed that Saturn, while calm and graceful in appearance, was in fact a dynamic and turbulent world full of surprises. Perhaps one of the most profound legacies of the Saturn encounters was how they expanded the sense of diversity in our solar system. With Jupiter, scientists had been amazed at the volcanic fury of Io and the hidden oceanic potential of Europa. Saturn built upon this by presenting Titan with its thick, lifelike atmosphere and Enceladus with hints of hidden activity. Suddenly, moons were no longer simple, inert rocks, but dynamic, varied worlds, each potentially harboring secrets about the conditions necessary for life. The Saturn encounters reinforced the idea that the solar system was not a place of uniformity, but one of staggering diversity, with every planet and moon telling a different story. For the public, the images and discoveries from Saturn were mesmerizing. The sight of Saturn's rings up close, with their countless shimmering bands, became some of the most iconic images ever taken by humanity's spacecraft. The ghostly beauty of Titan's atmosphere and the mysterious brightness of Enceladus gave people new worlds to dream about, while the discovery of strange ring spokes and the haunting visage of Iapetus added layers of mystery. Voyager's visit to Saturn was not just a scientific triumph. It was a cultural moment that deepened humanity's sense of wonder about the universe. As the spacecraft prepared to journey further outward, Saturn stood as a reminder that the cosmos is endlessly surprising, each destination offering revelations that redefine our understanding of what it means to explore. When Voyager 2 departed Saturn, it set course for Uranus, a planet that had remained little more than a faint bluish-green disk in the best Earth-based telescopes. Until 1986, Uranus was a mystery, its tilted rotation and faint rings barely understood, its moons mere points of light, with no detail. The arrival of Voyager 2 transformed this vague knowledge into a flood of discovery, forever changing how scientists viewed the outer planets. As the spacecraft approached, it revealed Uranus's bizarre axial tilt more vividly than ever. Unlike Earth, Jupiter or even Saturn, Uranus is tipped over on its side, with its rotational axis tilted at nearly 98 degrees. This meant that instead of spinning upright, the planet rolled along its orbit, creating the most extreme seasons in the solar system. One pole could bask in 42 years of continuous sunlight, while the other remained in 42 years of darkness, a cycle so strange that it challenged conventional models of planetary dynamics. This dramatic tilt might have been caused by a colossal collision with a planet-sized body early in its history, a violent event that not only tipped Uranus, but could have shaped its moons and rings as well. The atmosphere of Uranus proved just as unusual. Voyager 2's cameras captured a planet that appeared oddly bland compared to the stormy faces of Jupiter and Saturn. Its cloud tops looked smooth and featureless in visible light, with only subtle hints of banding or activity. But instruments capable of peering into infrared wavelengths told another story. Beneath the muted exterior, Uranus's atmosphere contained methane gas that absorbed red light, giving the planet its distinctive blue-green color. Hidden within were layers of cloud decks made of methane ice, hydrogen and helium, along with faint signatures of dynamic processes that hinted at weather more active than the calm appearance suggested. Later studies would confirm that Uranus does host powerful winds and even massive storms, but Voyager's snapshots gave the first glimpse of this deceptively calm world. Voyager also revealed Uranus's faint and delicate ring system in astonishing detail. Previously detected only by Earth-based telescopes in 1977, these rings had been a mystery, their composition and structure largely unknown. The spacecraft showed that Uranus's rings were dark, narrow, and composed mostly of small, dusty particles. Unlike Saturn's bright, icy rings, Uranus's rings absorbed most of the sunlight that struck them, making them appear almost black. Their narrowness suggested that tiny shepherd moons were keeping them confined, a delicate balance between gravity and motion. Voyager identified at least 10 distinct rings, each one unique in structure, showing that even this far-flung planet had a surprisingly complex system surrounding it. Perhaps the most remarkable discoveries, however, came from Uranus's moons. Before Voyager, only 5 were known: Miranda, Ariel, Umbriel, Titania, and Oberon, and all were assumed to be cold, cratered, and inactive. Instead, Voyager revealed worlds far stranger and more diverse than anyone had expected. Miranda, the smallest of the 5, turned out to be one of the most unusual objects in the solar system. Its surface looked like a patchwork quilt, with giant canyons, ridges, and strange geometric patterns. Some regions appeared relatively young, suggesting resurfacing had occurred, possibly driven by internal processes like tidal heating. Ariel surprised scientists with evidence of flowing material, possibly frozen liquids, across its surface, hinting at past geological activity. Umbriel appeared darker and older, scarred by ancient impacts, while Titania and Oberon displayed towering fault valleys and mysterious surface features, proving that even these distant moons had experienced dramatic geological histories. The sheer diversity of landscapes on Uranus's moons was a revelation, showing that geological activity was not confined to the inner solar system or the larger moons of Jupiter and Saturn. Voyager's flyby of Uranus was also the first time humanity encountered a planet's magnetic field that was so misaligned and unusual. Instead of being centered and aligned with its rotational axis, Uranus's magnetic field was both tilted at 59 degrees and offset from the planet's center. This created a lopsided magnetosphere that wobbled dramatically as Uranus rotated, unlike anything scientists had seen before. The discovery suggested that the magnetic field was generated in a shallower region of the planet's interior rather than deep in a metallic core, challenging standard models of planetary magnetism. This bizarre magnetic setup not only shaped Uranus's space environment, but also had profound implications for understanding how magnetic fields form on other worlds. For the public, Uranus might not have delivered the same iconic imagery as Jupiter's raging storms or Saturn's shimmering rings, but the encounter was no less historic. It transformed a dim, distant world into a place of strange beauty, mystery, and complexity. Voyager showed that even in the farthest reaches of the solar system, planets and moons defied expectations, each with its own surprises waiting to be uncovered. Uranus became a reminder that the solar system is not uniform but filled with variety, shaped by chance collisions, hidden forces, and ancient histories. As Voyager 2 sped onward to Neptune, it carried with it the knowledge that every stop on its journey would rewrite the textbooks, and Uranus had proven that even the seemingly quietest planets could hold secrets that astonished the world. After leaving Uranus behind, Voyager 2 pressed on toward Neptune, a planet that had been little more than a distant blue speck through the eyes of telescopes on Earth. By 1989, anticipation was high, as Neptune represented the last unvisited planet of the solar system, and Voyager's flyby would be humanity's only chance to glimpse it up close for decades, if not centuries. As the spacecraft closed the gap, Neptune began to reveal itself as a world far more dynamic and surprising than scientists had dared imagine. Unlike Uranus, which had appeared subdued and bland, Neptune was alive with motion. Its atmosphere crackled with activity, filled with the fastest winds ever recorded in the solar system, reaching up to 1,200 miles per hour. These jet streams, moving faster than the speed of sound on Earth, defied expectations because Neptune receives far less sunlight than the gas giants closer to the sun. Somehow, it generated enough internal heat to power storms that rivaled Jupiter's Great Red Spot in intensity. Voyager's cameras revealed the now famous Great Dark Spot, a massive storm system roughly the size of Earth, swirling in Neptune's upper atmosphere. Nearby, smaller storms spun across the planet's surface, including the Scooter, a bright white cloud racing around the globe at breakneck speed. The discovery of these storms painted Neptune not as a cold, lifeless sphere, but as a planet of violent weather and raw energy. Voyager also provided unprecedented insight into Neptune's atmospheric composition. Like Uranus, the planet's blue hue came from methane absorbing red light and reflecting blue wavelengths, but the intensity of the color was deeper and richer, suggesting additional processes at work. Methane ice clouds drifted across the skies, and Voyager's instruments detected a layered atmosphere filled with hydrogen, helium, and trace hydrocarbons. Despite Neptune's distance from the Sun, its atmosphere churned with surprising activity, pointing to a powerful internal heat source. This raised questions that scientists are still trying to answer. How does Neptune, so far from the Sun's warmth, generate such dynamic weather systems. Voyager's data hinted that the planet emits more than twice as much heat as it receives, suggesting that its interior might be far hotter than expected, possibly due to leftover energy from its formation or exotic processes deep within. Neptune's rings, faint and elusive, also came into sharper focus. First detected only a few years earlier from Earth-based observations, their existence had been debated until Voyager's cameras confirmed them beyond doubt. These rings were thin, dark, and incomplete in appearance, forming arcs rather than continuous bands. This discovery was baffling, as scientists had assumed that planetary rings should distribute evenly over time. The arcs appeared to be maintained by the gravitational influence of small shepherd moons, keeping the material confined in clumps rather than spreading out. Voyager captured stunning images of these rings, showing that even the farthest giant planet carried its own unique signature of beauty, distinct from the majestic rings of Saturn or the narrow bands around Uranus. Perhaps the most astonishing revelations came from Neptune's largest moon, Triton. Voyager's close flyby transformed Triton from a cold, dim point of light into one of the most extraordinary worlds in the solar system. Against expectations, Triton was geologically active, with geysers erupting nitrogen gas high into its thin atmosphere, leaving dark streaks across its icy surface. No one had anticipated that such a distant moon, orbiting in the frigid outer reaches of the solar system, could still be alive with activity. Voyager revealed a surface of frozen nitrogen and water ice, sculpted by cryovolcanism, tectonics, and mysterious processes unlike anything seen before. Some regions appeared smooth and young, while others were scarred by strange cantaloupe-like textures unique in the solar system. Triton's retrograde orbit, moving opposite to Neptune's rotation, added to the mystery, strongly suggesting that Triton was once a captured object, likely a former Kuiper Belt body pulled into Neptune's gravity long ago. This capture event may have destabilized Neptune's system in the distant past, reshaping its moons and rings. Voyager's encounter with Neptune was not just a triumph of engineering and science, but also a bittersweet milestone. It marked the end of humanity's first grand tour of the planets. From Jupiter's storms to Saturn's rings, from Uranus's tilted axis to Neptune's howling winds, Voyager had rewritten the story of the solar system with every encounter. At Neptune, it delivered a finale that exceeded all expectations. The images of the great dark spot, the breathtaking view of Triton's geysers, and the haunting beauty of Neptune's distant blue orb captured the imagination of the world. As Voyager sped away from Neptune, it carried with it the last close-up observations of a planet humanity would see for generations. It had revealed a world of extremes, a place where supersonic winds roared across an ice giant's atmosphere, where rings defied logic, and where a moon billions of miles from the sun somehow remained active and alive. The flyby of Neptune reminded humanity of the boundless variety and unpredictability of the cosmos, proving once again that even in the farthest, coldest reaches of our solar system, the universe could surprise us with beauty and wonder beyond imagination. When Voyager 2 left Neptune behind in 1989, its primary mission had reached a natural conclusion. It had done what it was designed to do: complete the grand tour of the outer planets, giving humanity its first close encounters with worlds we had only glimpsed as distant dots through telescopes. Yet, rather than shutting down, Voyager entered a new phase of exploration, one that would take it into regions of space no spacecraft had ever traveled. This became known as the Voyager Interstellar Mission, and it was about venturing beyond the planetary system into the vast, largely uncharted frontier of interstellar space. For scientists, this phase represented both a challenge and an opportunity to use the spacecraft's still-functioning instruments to gather data about the outer boundaries of the sun's influence, the heliosphere, and ultimately the conditions in the space between stars. For humanity, it was the symbolic continuation of our drive to go further, to push beyond horizons that once seemed unreachable. Voyager 2, along with its twin Voyager 1, had crossed into a domain where the sun's influence wanes and the interstellar medium begins to dominate. This region, called the heliosphere, is shaped by the solar wind, a stream of charged particles constantly flowing outward from the sun. The outer edge of this bubble is where the solar wind slows and is pushed back by the pressure of particles and magnetic fields from interstellar space. Voyager's instruments measured these subtle changes, giving us direct evidence of how our solar system interacts with the wider galaxy. Long before it actually crossed into interstellar space, Voyager provided critical insights into the nature of cosmic rays, magnetic fields, and the density of charged particles at the solar system's edge. These measurements reshaped scientific understanding of how solar activity influences space environments far beyond the orbit of Pluto. Though originally designed to study planets, Voyager's instruments proved surprisingly versatile in this new role. Its plasma detector, magnetometer, cosmic ray sensors, and low-energy charged particle detectors became crucial tools for understanding the heliopause, the boundary where the solar wind and interstellar medium meet. In 2012, Voyager 1 famously crossed that boundary, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, providing confirmation that the crossing was real and not just an anomaly. These milestones marked a turning point in space exploration, demonstrating that spacecraft launched in the 1970s were still capable of delivering groundbreaking science nearly half a century later. But Voyager's interstellar mission is not purely scientific. It carries a deeper human story. On board both Voyagers is the Golden Record, a carefully crafted time capsule designed to tell any potential extraterrestrial civilization about Earth and its inhabitants. The record includes greetings in multiple languages, sounds of nature, music from diverse cultures, and images depicting life on our planet. As Voyager drifts ever farther into interstellar space, it becomes not just a scientific probe, but also a cultural ambassador, carrying humanity's story into the cosmos. The Golden Record is a reminder that exploration is not just about gathering data, but about leaving a trace of who we are and what we value. The spacecraft itself is a testament to human ingenuity and persistence. Operating decades beyond its expected lifespan, Voyager continues to send back faint signals relayed across billions of miles through NASA's Deep Space Network. Each transmission takes more than 18 hours to reach Earth, yet the spacecraft's instruments continue to function despite the harsh environment of deep space and the dwindling supply of power from its nuclear batteries. Engineers have devised ingenious ways to conserve energy, shutting down non-essential systems and prioritizing scientific instruments. These efforts reflect not only technical brilliance, but also a profound commitment to keeping the mission alive for as long as possible. The significance of the Voyager interstellar mission lies not only in the data it collects, but in the perspective it provides. For the first time, humanity has a direct connection to interstellar space, a region that has always been the backdrop of our night skies, but never accessible to us. Through Voyager, we are beginning to understand the galactic environment that surrounds our solar system, and by extension, the conditions that influence every star and planet in the Milky Way. These discoveries will shape future missions designed specifically to study interstellar space, but Voyager will always be remembered as the pioneer that first crossed the threshold. As it continues its silent journey outward, Voyager carries with it the hopes and imagination of those who built it, and of the countless people inspired by its story. Its path reminds us that exploration does not end when a mission objective is complete. Instead, exploration is an open-ended journey, one that continues as long as we are willing to listen to the faint signals returning from the edge of the unknown. Voyager's interstellar mission is a living symbol of human curiosity, resilience, and our desire to be part of something larger than ourselves. It demonstrates that even the smallest emissary of humanity, no bigger than a small car, can represent us to the galaxy, and in doing so it extends our presence far beyond the cradle of Earth. When we think of Voyager 2's journey, it is easy to picture a spacecraft slowly drifting through the emptiness of deep space, its instruments quietly collecting data as it sails further from Earth. Yet the story of this remarkable machine is not just about the science it delivers, but about its enduring legacy, the cultural impact it has had on generations, and the way it continues to redefine what humanity is capable of achieving. Section after section of its mission history reveals groundbreaking discoveries, but the seventh layer of its story is about reflection. What it means that a spacecraft launched in 1977, originally designed for a 5-year mission to study the outer planets, is still traveling nearly half a century later, carrying with it both hard science and symbolic meaning that extends far beyond astrophysics. Voyager 2 is no longer simply a machine, it has become part of the human narrative, a cosmic ambassador whose presence in interstellar space bridges science, philosophy, and culture in a way that no other mission has done before. One of the most profound aspects of Voyager's legacy is the way it reshaped how we view ourselves. When Voyager 1 turned its camera back toward Earth in 1990 at the request of Carl Sagan, it captured the iconic pale blue dot image. Though it was Voyager 1 that took that specific photograph, the symbolic meaning extended to its twin, Voyager 2, because together they represent humanity's boldest leap into the unknown. That tiny speck in the vast darkness became a universal reminder of how fragile and small our world is compared to the immensity of the cosmos. It was a lesson in humility, but also a powerful testament to what humans can accomplish when driven by curiosity and cooperation. Voyager 2's continued mission in interstellar space reinforces that lesson every single day. Each faint signal received across billions of kilometers tells us not only about plasma waves or cosmic rays, but also about the persistence of a civilization determined to reach beyond its limits. Culturally, Voyager has transcended science and entered the realm of art, literature, and imagination. Countless books, films, and pieces of music have drawn inspiration from its journey, often using it as a metaphor for exploration, isolation, or hope. The Golden Record in particular has become one of the most famous artifacts of the 20th century. It is not just a scientific experiment, but a statement about humanity's desire to communicate across time and space, to say to the universe, "We were here and this is what we were like." That combination of science and storytelling has kept Voyager alive in the public imagination long after its planetary encounters ended. For many, Voyager is not simply a probe. It is a messenger carrying the essence of humanity into realms where no person can yet travel. Another part of its enduring legacy lies in the way it paved the road for future missions. The techniques developed to extend Voyager's lifespan, the methods for conserving power, and the reliance on global communication networks have influenced mission planning for other spacecraft, from the Cassini probe at Saturn to the New Horizons mission that flew past Pluto. Voyager's endurance proves that with careful engineering and ingenuity, spacecraft can continue functioning far beyond their original design lifespans. This lesson is invaluable as humanity looks toward more ambitious missions, including sending probes to other stars. In many ways, Voyager is the prototype of interstellar exploration, and its success shows that humanity's reach does not have to be confined to its solar system. Perhaps the most striking element of Voyager's legacy is its symbolic role in uniting humanity around a common achievement. Space exploration often carries political undertones, but the Voyagers have largely transcended that, becoming shared symbols of human potential. People across the globe, regardless of nationality, have looked up at the night sky, knowing that two small spacecraft launched from Earth are now sailing among the stars. That sense of collective ownership fosters a rare feeling of unity, reminding us that while borders and divisions exist on Earth, in the context of the universe we are one species, sharing one fragile planet. Voyager embodies that shared identity better than almost any other scientific endeavor, because it represents all of humanity, not just the nation that built it. Voyager's story continues to resonate because it is not just about exploration of space, but exploration of meaning. The data it transmits from interstellar space is invaluable, but so too is the inspiration it provides to students, scientists, and dreamers. It tells us that perseverance pays off, that boundaries can be broken, and that even the faintest signal traveling across billions of kilometers carries with it a message of resilience. Voyager 2's endurance is proof that humanity is capable of leaving behind artifacts that will outlast entire civilizations. Long after its instruments stop transmitting, it will continue its silent journey, carrying the golden record, perhaps for billions of years, into the galaxy. In that sense, Voyager is more than a mission. It is humanity's first true interstellar footprint, a piece of our story written into the fabric of the cosmos. And that legacy will remain, no matter how distant the spacecraft becomes or how faint its voice grows. A permanent reminder that we dared to reach for the stars and succeeded. As Voyager 2 ventured beyond the planets it was designed to explore, it entered a new frontier, one no spacecraft had ever crossed before, the outermost boundaries of the heliosphere, where the solar wind meets the interstellar medium. This region, often referred to as the heliopause, represents the edge of the sun's influence and the beginning of true interstellar space. For decades, scientists had debated what this boundary might look like, how sharp or diffuse it would be, and what kind of physics governed its structure. Voyager 2's passage through this region provided answers to long-standing questions, while also raising entirely new ones, giving us the most direct insight ever obtained into the relationship between our solar system and the broader galaxy. What makes this achievement extraordinary is that Voyager 2 not only confirmed earlier findings from its twin, Voyager 1, but also revealed critical differences that proved the heliosphere is not uniform, but instead dynamic and asymmetric, shaped by powerful and complex forces. When Voyager 2 crossed into interstellar space in November 2018, it was already more than 11 billion miles from Earth. The spacecraft's instruments, remarkably still functioning after more than 40 years, recorded the drop in solar wind particle density and the corresponding rise in interstellar plasma particles. Unlike Voyager 1, which had lost its plasma instrument decades earlier, Voyager 2 was able to directly measure the properties of the charged particles beyond the heliopause, giving researchers unprecedented data about the density, pressure, and temperature of the interstellar medium. This was one of the most critical contributions of the mission's extended journey, because it allowed scientists to better understand how the Sun interacts with the galaxy around it. The discovery that interstellar plasma is denser than expected challenged previous models and suggested that the heliosphere might act as a protective bubble, shielding our solar system from cosmic rays and high-energy particles, but in a more complex way than anyone had imagined. Another revelation from Voyager 2's crossing was the shape of the heliosphere itself. For years, scientists had pictured it as a teardrop-shaped bubble, compressed on one side by the interstellar medium and stretched on the other like a comet's tail. However, the timing of Voyager 1 and Voyager 2's respective exits from the heliosphere at different distances and in different directions indicated that the boundary is not smooth or symmetrical. Instead, it appears to be distorted by external pressures, possibly from nearby supernova remnants or magnetic fields in the local galactic environment. Voyager 2's observations suggested that the sun's bubble is constantly shifting, compressed and stretched by changing interstellar conditions. This new understanding not only changes how we visualize the solar system's place in the galaxy, but also informs models of how cosmic radiation interacts with planetary atmospheres, including Earth's, which has direct implications for space travel and planetary habitability. Perhaps most importantly, Voyager 2's data gave scientists the first comparative measurements of the heliopause. By having two spacecraft in different regions of the boundary, researchers were able to compare and contrast the local environments. The differences confirmed that the heliosphere is far more dynamic and irregular than previously thought. For example, Voyager 2 measured a sharper transition at the boundary compared to Voyager 1, where the shift in particle densities was more gradual. This suggested that the heliopause is not a fixed, well-defined surface, but more like a turbulent frontier shaped by constantly changing pressures between solar and galactic forces. These findings force us to rethink what it means for a spacecraft to leave the solar system, since the boundary is less a wall and more a fluctuating frontier. Voyager 2's passage into interstellar space also sparked renewed questions about the larger galactic environment. Scientists now believe that studying the interstellar medium is critical, not just for understanding our place in the galaxy, but also for making predictions about how other planetary systems evolve. The data from Voyager 2 provided the first direct evidence of how local interstellar conditions might affect star systems and their protective magnetic bubbles. This has implications for astrobiology, since the ability of a planetary system to shield itself from cosmic rays could influence the development and sustainability of life. In this way, Voyager 2 is helping to bridge the fields of planetary science, astrophysics, and the search for life beyond Earth, all through the study of a faint plasma signal billions of miles away. What makes this chapter of Voyager 2's story so compelling is that it represents not just a continuation of exploration, but the crossing into a new era of discovery. The spacecraft is now a true interstellar probe, collecting data from a region that no human-made object has ever visited. Its instruments, though aging, are providing direct evidence of phenomena that were once the subject of speculation and theory alone. And every new transmission received, faint and delayed by nearly 18 hours of travel time at the speed of light, adds to our understanding of how the Sun, Earth, and all the planets are connected to the wider galaxy. Voyager 2's journey beyond the heliopause has become one of the most profound milestones in the history of science, because it shows us that exploration does not end at the edge of our solar system, it merely begins there. The survival of Voyager 2 over more than 4 decades is nothing short of miraculous, and its endurance has become one of the most compelling aspects of the entire mission. Originally designed to last only a few years, just long enough to conduct flybys of Jupiter and Saturn, the spacecraft has now surpassed every expectation, continuing to function billions of miles from Earth under conditions no engineer could have fully anticipated. Its journey through the cold vacuum of interstellar space has revealed not just new scientific frontiers, but also the extraordinary resilience of human engineering, when combined with careful management, ingenuity, and a determination to keep the mission alive for as long as possible. Voyager 2's survival is a story of technological triumph, scientific persistence, and a reminder of what happens when humanity dares to push its limits far beyond the horizon. At the heart of its survival is the spacecraft's power source, the radioisotope thermoelectric generator, RTG, which converts the heat from decaying plutonium-238 into electricity. When Voyager 2 launched in 1977, the RTG produced about 470 watts of power, but each year that output has dropped steadily as the fuel decays. Today, the spacecraft runs on less than half that amount, forcing mission controllers to make difficult choices about which instruments to keep operating and which to shut down in order to conserve power. In many ways, this balancing act is like keeping an elderly patient alive with limited resources, carefully managing energy flow to essential systems such as communications, thermal regulation, and the scientific instruments still providing groundbreaking data. That Voyager 2 continues to operate under these constraints is a testament to both the durability of its original design and the skill of the teams at NASA, who have found creative ways to stretch its capabilities far beyond their intended lifespan. Communication is another miracle of endurance. At more than 12 billion miles from Earth, Voyager 2 transmits signals that are so faint they carry less power than a refrigerator light bulb. These signals take nearly 18 hours to reach Earth, where they are captured by the giant antennas of NASA's Deep Space Network. Maintaining contact with the spacecraft requires extraordinary precision, since even the smallest misalignment in its high-gain antenna would cause the signal to vanish into the void. Engineers have performed course corrections and adjustments using tiny thrusters that were not meant to fire for decades, yet still function. The fact that these thrusters continue to operate after spending so long in the harsh environment of space, exposed to radiation, freezing temperatures, and micrometeoroid impacts, is a tribute to the craftsmanship of their construction. Every successful communication is a reminder that Voyager 2 is not lost. It is still faithfully reporting from the edge of the galaxy, holding a fragile but steady link between humanity and the stars. Beyond the technical marvel, Voyager 2's survival also represents a philosophical triumph. It embodies the idea that exploration is not just about immediate rewards, but about endurance and persistence. Every year, the spacecraft continues to operate, adds to humanity's collective knowledge, turning what was once a short-term planetary mission into a multi-generational journey. Scientists who were not yet born when Voyager launched now work with its data, proving that missions like this extend far beyond the careers of the people who created them. Voyager 2 is not just surviving, it is creating a legacy that bridges generations, cultures, and even disciplines of science. Its continued presence reminds us that exploration is as much about patience and resilience as it is about discovery. Voyager 2's endurance also inspires reflection on the future of exploration. If a spacecraft built in the 1970s with technology less advanced than today's smartphones can last this long and travel this far, what might future probes achieve with the benefit of modern engineering and power systems? Concepts like interstellar probes, advanced propulsion, and long-duration robotic explorers are being designed today with the hope of learning from Voyager's resilience. The spacecraft's survival is a roadmap showing what is possible when durability, careful planning, and adaptive problem-solving are combined. In the end, the survival of Voyager 2 is as much a human story as it is a technological one. It is about the people who designed it, the teams who have nursed it through countless challenges, and the generations who have watched it cross from one frontier to another. It has endured, not because it was flawless, but because of the creativity and persistence of those who refused to let it fade quietly into the void. Each additional day it continues to function is a small miracle, a reminder that humanity's reach does not end at Earth, or even at the planets, but extends outward into the galaxy itself. Voyager 2's survival is proof that even in the cold, silent darkness of interstellar space, the spark of human curiosity can endure for decades, carrying our questions, our ingenuity, and our legacy far beyond the boundaries of home. As Voyager 2 approaches the final chapter of its extraordinary journey, its story becomes less about what new discoveries it will make, and more about what it symbolizes for humanity. Launched in 1977, it has already exceeded its expected mission duration, by more than 40 years, delivering data from the outer planets, their moons, and now from interstellar space itself. But as its power supply dwindles and the signals grow weaker, scientists and engineers know that this mission is nearing its inevitable conclusion. This reality, however, does not diminish its importance. In fact, it makes the mission even more profound. The approaching end of Voyager 2 is not a story of loss, but of legacy, a reminder that exploration is a journey without a fixed destination, and that even as the spacecraft drifts silently into the void, its contributions will continue to echo for centuries. One of the central truths about Voyager 2's final years is that it continues to work against impossible odds. With each passing year, the RTG power decreases, forcing NASA to shut down one instrument after another. Eventually, even communications will have to be sacrificed, and the spacecraft will fall silent. When that happens, Voyager 2 will become what it was always destined to be, a wanderer, endlessly drifting between the stars. Yet silence does not mean irrelevance. Even after its systems shut down, it will still carry the golden record, a time capsule of humanity encoded in music, greetings, and sounds from Earth. That record transforms Voyager 2 from just a scientific mission into a cultural ambassador. Long after Earth has changed beyond recognition, Voyager 2 will still be out there, a silent messenger bearing evidence that humanity once existed, once dreamed, and once reached for the stars. This final phase of the mission also reflects the human side of exploration. Scientists and engineers who have dedicated their careers to Voyager often describe it as a companion, something they check on daily, something that has shared decades of milestones with them. For many, letting go of Voyager 2 will feel like saying goodbye to an old friend. But this farewell is softened by the understanding that the mission has given humanity more than anyone could have imagined. From the breathtaking images of Uranus and Neptune worlds that no other spacecraft has visited, to the current data streaming in from interstellar space, Voyager 2 has expanded the borders of human knowledge in ways that are still being processed today. Its legacy will live on not only in the data, but in the very idea that humanity can build machines that outlast generations and continue to function faithfully, even in the harshest environments imaginable. The approaching silence of Voyager 2 also sparks reflection about the future of exploration. What comes after this mission? Engineers and scientists are already thinking about new spacecraft capable of reaching farther, powered by technologies that could make voyages like Voyager's seem modest in comparison. Concepts such as solar sails, fusion propulsion, and even miniaturized probes designed to travel to nearby star systems are being actively researched. Voyager 2's success lays the foundation for all of these efforts, proving that humanity has both the will and the skill to send our creations beyond the solar system. Its final message may not just be the last transmission of data, but an invitation to keep pushing forward, to keep building, to keep imagining. Ultimately, the approaching end of Voyager 2 reminds us of something deeper, that exploration is not about permanence, but about impact. No spacecraft lasts forever, but their achievements endure in human memory, in scientific records, and in the inspiration they give to future generations. Voyager 2's journey is a living story of endurance, discovery, and vision. Even as its instruments go dark and its voice fades into silence, its mission will never truly end. For as long as it drifts through the stars carrying its message from Earth, it will remain a beacon of what humanity can achieve when it dares to reach beyond the horizon. In the end, Voyager 2's story is not one of finality, but of continuity, a symbol that even in the quiet of space, the echoes of human curiosity will travel on, timeless and unbroken. As the story of Voyager 2 approaches its inevitable conclusion, we are reminded that the mission was never simply about a spacecraft. It has always been about humanity's ability to dream beyond the limits of what seemed possible. Launched in 1977 with the modest goal of exploring the outer planets, Voyager 2 went on to surpass every expectation, carrying human ingenuity farther than any machine before it, and delivering knowledge that reshaped our understanding of the solar system. Its passage through Jupiter, Saturn, Uranus, and Neptune revealed worlds of stunning complexity, moons of unexpected activity, and planetary systems that challenged long-held assumptions. Those moments of discovery were not just scientific triumphs, but also cultural milestones, events that unified people across the globe in shared awe. Now, as Voyager 2 drifts farther from Earth, its power dwindling and its instruments gradually falling silent, we face not the end of its story, but the continuation of its journey in a new form, one that symbolizes endurance, legacy, and the eternal human drive to explore. The conclusion of Voyager 2's active mission invites us to reflect on what it has taught us beyond data and images. Its endurance over more than 4 decades speaks to the ingenuity and foresight of the scientists and engineers who built it, many of whom never imagined their creation would still be operating in interstellar space. It shows us that the human capacity to innovate is not bound by immediate results, but can extend across generations, creating legacies that outlast their makers. Voyager 2 has become a bridge across time, linking the optimism of the 1970s space age with the technological ambitions of today and the scientific frontiers of tomorrow. It proves that exploration is not a passing impulse but a defining feature of our species, one that compels us to send our voices and machines into the unknown with the hope that something or someone will hear them. The spacecraft's golden record, often spoken of with a mix of poetry and practicality, encapsulates this idea perfectly. While the scientific instruments of Voyager 2 will eventually power down, the record will remain intact, carrying the sounds of Earth greetings in multiple languages, music, and even the sound of human laughter through the galaxy. It is not meant to be practical, it is meant to be hopeful, a declaration that we are here, that we existed, and that we reached for the stars. In this way, Voyager 2 becomes more than a scientific instrument. It becomes a cultural artifact, a monument of human imagination that will outlive every city, every civilization, and perhaps even Earth itself. Long after our species has moved on to other worlds or faded into history, Voyager 2 will continue its silent trajectory, a lone messenger bearing witness to what we once dared to do. The end of the mission also directs our gaze toward the future. Voyager 2's success sets the stage for even more ambitious endeavors. Already, projects like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory are extending our reach into the cosmos, and concepts for interstellar probes are being developed that may one day follow in Voyager's path, but with far greater capabilities. Voyager 2 demonstrated that interstellar exploration is possible, not just in theory, but in practice. It cracked open a door that can never be closed again. Its legacy is not just the knowledge it gathered, but the inspiration it provides for all who come after. Every future mission to the outer planets, every concept for traveling to another star, and every dream of interstellar travel owes something to Voyager 2's pioneering journey. In the end, the conclusion of Voyager 2's active mission is less about mourning the silence that will eventually come, and more about celebrating the story it tells. It is a story of discovery that began on a launch pad in 1977 and now stretches beyond the edge of our solar system, farther than any human creation has ever traveled. It is a story of endurance against the unimaginable cold and radiation of space. It is a story of legacy, of a machine that carries both scientific instruments and a cultural time capsule into the unknown. And most importantly, it is a story of us, our curiosity, our imagination, and our willingness to push past every boundary. As Voyager 2 continues its endless voyage into interstellar space, it leaves behind more than data. It leaves behind a challenge, a reminder, and a promise. The challenge is to keep exploring. The reminder is that we are capable of achievements far greater than we believe. And the promise is that the echoes of human curiosity will continue to travel through the stars long after the spacecraft itself falls silent. In this sense, Voyager 2 will never truly conclude, because its mission is eternal, to carry the essence of humanity into the vastness of the cosmos.